Hello, it's my pleasure to introduce this afternoon's session. And this has been my dream for a long time, that I3D would have whole sessions on ray tracing, which are long. So we're living in the golden age of graphics is what that means. Our first speaker, where are you? Oh, there you go. Is Atsushi Yashimura from AMD. His co-author Takahiro Harada is also from AMD and is also here. Atsushi is based in Tokyo and his comrade is based in California. And their talk is on culling for ray box intersection. It's long been a problem. I'll do a little of your intro. That axis aligned BBHs are super fast, but they're not tight. And this is trying to get the advantages of axis aligned. So I'm delighted to see this work. It's something I've worked on before and failed. So hats off.
Thank you for introducing me. Hello, I'm Atsushi Yoshimura at the AMD Advanced Rendering Research Group. I'm going to introduce our paper, Subspace Culling for Laybox Intersection. So first, let me introduce from the problem setting what we want to solve. Needless to say, ABB is a popular bounding volume, especially it's a de facto standard bounding volume on BBH for ray tracing. This is because of the simple representation, also the cheap intersection with array, and there are a bunch of well-matured methods to build a high-quality BBH. These are very strong reasons to choose ABB for the bounding volume. However, ABB may not be able to tightly bound geometry in some cases. For example, like this. Thin and tilted triangle on the left or sparse triangles on the right. As you can see, these are so much empty space, which causes a lot of false positive hits during BBH traversal. Ray BBH intersection can be slower due to traversal of too many nodes. It's not a corner case. For example, here and far geometry like this, they can be very thin and often it's not axis aligned. So we will tackle against this kind of situation. First, let me have a look at a simple toy experiment. Let's say there is a triangle enclosed by an ABB and shoot random rays towards the ABB and count how many rays do not hit the triangle despite they hit the ABB. Then we can know the false positive ratio in this case. In 3D, it's the roughly visualization of what we did. Can you imagine how much it is? Actually, false positives can be over 70%. Of course, it depends on the triangle, but this is a bit surprising. There should be some possibility of better culling. In order to do much better culling, bounding volume selection is a very large factor. Of course, there are some choices for alternative bounding volume other than ABB. For example, OBB, KDOP, KODPs, and ellipsoid capsule, convex hull, etc. These culling capability looks gravitate, but they have more computational overhead, and also they have larger memory consumption. Some of them are struggling to build high-quality BBH efficiently. I believe OBB is a great candidate as concurrent work. as a concurrent work, Bitsas et al. Proposed a parallel parallel OBB tree construction. However, the storage space and the traversal costs still have to be paid as drawbacks. So in terms of our goal, we want to find out a way to achieve these things. First, cause false positives more than ABB, and small computational overhead. For culling, also small memory footprint. Finally, it should have a simple and fast BVH construction. Instead of other bounding volumes, we use voxel data structure toward our goals because voxels have nice properties for us. First, it can fit densely to the primitive as long as the grid resolution is fine enough. Just like this. Even though the grid size is 4x4x4, as shown as here, you can see it can bound the triangle more tightly. Second, the data structure can be very simple. 1 bit per cell is used to represent its occupancy. And third, there is an efficient way to intersect with rays. Digital differential analyzer, DDA-like iterative method is a good candidate for such case. But we use a lat-based approach instead because it's all one complexity and it requires only a few arithmetic operations. I will discuss it a bit more. The idea is to use bitwise AND operation. It is proposed in an article by Holger Gruen in GPU Pro 360. Array versus a small grid test can be conservatively replaced by bitwise AND. Let's say ABB has a specific pattern like this to describe occupancy. Then the ray traversal on the volume also can be described voxels as a voxel like this, its footprint. Finally, the bitwise AND of ABB mask and the ray mask on the right can describe the intersection. Thus, we can check the all bits are if the all bits are 0 or not. If all bits are 0, it means no hit. Actually, before this intersection, we have to build the voxel pattern for the ray, but we can. But the ray mask can be pre-computed as a lookup table so that we can make it all one. In general cases, it takes linear time complexity to build a voxel pattern from array by using a DDA-like method. But we can use a lookup table approach as an approximation for our case. The table key is the voxel indices of ray origin and ray end. Use the locations as a key to fetch the ray mask. The fetched voxel pattern is like this. That's it. The table itself can be constructed before traversal, so we can get the ray mask pattern without iterative method. But you may notice that the voxel pattern can be a bit wider than the DDA-like method. It's because the table resolution is limited. But our goal is early culling, so it's still safe as long as it's conservative. Despite the false positives here, the hash-based approach is faster in overall performance in our experiment. The paper has more detailed experimental results with experimental results about the side effect of the approximation. Please check the details on our paper. So this is a short summary of the approach. Use voxels for one step more culling after the AAVV intersection. First, we check AAVV intersection as usual. And after that, we propose to do voxel culling with lookup table approach so that the false positive rays are rejected by just a few memory lookups and bitwise AND operations. Our culling can be embedded with a very straightforward way. This is a classical classical BBH traversal loop. Here is outside traversal loop, and first we'll pop a node from a stack and process a leaf node and perform intersections against the AVVs and push children's if it's hit. And here, what's new for our method is the red highlighted section. Just add extra condition before pushing an intersected child. First, get the object mask from the AVV. Second, build array mask from the hit point on the AVV. Finally, we take our bitwise AND operation with them. If it has no overlap, then we can skip the child earlier. So we introduced our intersection approach, but what about voxel construction in BBH? There are a lot of AVVs in a hierarchy, and they all want to have proper voxels. Let's think about the best of voxel mask for the top node. Actually, the best mask can be computed by a brute force approach, which visits all triangles below and check the voxel occupancy. But in this case, top node on a figure contains all of the triangles, so the exact occupancy requires visit many triangles in children below. It's obviously expensive, so we don't want to do that. What can we do? One thing is that we can do is to approximate the occupancy by voxels. Let's say there are several triangles like this, and these are two children. The left node has 4 triangles, and the right one has 3 triangles. Then why don't you just use the voxels as approximated occupancy? Yeah. Then we can calculate the mask from the children's voxels without knowing their triangles. From the perspective of the tree structure on the right, we only need to consider its direct children of the target node. So we don't have to traverse lower level of the data structure, which reduces the construction cost. So by using approximated occupancy, we can get similar result with lower cost as we saw earlier. Since it's just an approximation, there is a trade-offs between the exact occupancy versus approximated occupancy. A way to control the accuracy is how many levels we will go down. Let's see on the left, we can take the occupancy from the direct children, but the approximation may be too rough. On the other hand, on the right, box cells 2 levels below are used for the approximation as they have finer box cells so that it represents a more accurate occupancy, but need more nodes to visit. We have a discussion about the trade-offs with measurements on the paper, so please check it for more details. By the way, how much memory do we need for the box cells? It's actually straightforward. 4x4x4 case takes 8 bytes, and the 6x6x6 case takes 27 bytes. So this is a visualization of the memory size with 4x4x4 case with a classical BVH inner node, where each cell is 4 bytes. Actually, it takes a bit too much memory, so we would like to think about box cell compression. There is a good news. The bit patterns are not just random. I mean, there are some frequently used mask patterns. So we can use a simple lookup table approach. First, we make a small table with the frequently used mask. And let's say there are 256 elements there, so that the index of the table can be represented by just 1 byte. So we can simply store the index into the BVH node. It's very simple, but we observed it works very well. And one more good thing is that it is box cell resolution independent. The storage size only depends on the table size. So even if 6x6x6 box cells can be compressed into just 1 byte, which is 1/27th of their original size. Technically speaking, the frequency of the mask buttons for the prioritization is not optimal because it does not take the spatial property of each node into account. So we also propose SAH-based prioritization on our paper. So please check more details on the paper. We evaluated our method with several scenes. We checked the number of intersections to see culling efficiency, also measured total rendering performance. First, we measured the number of intersections. There are several variations of measurements on the paper, but here, let me focus on the configuration to avoid complexity, where box cell resolutions are 4x4x4 or 6x6x6. For object mask, we use only 1 byte per ABB by the RAT-based compression. And for culling, we use DDL-based exact culling for measuring the box cell culling capability. The table here is showing the relative intersections compared to the baseline, which is no culling. Lower is better. For example, 50% means that the raycast is done only with half number of intersections. As summary of the table, from 9 to 38% of the intersections are reduced with resolution 4x4x4 case, and from 12 to 46% of the intersections are reduced with resolution 6x6x6 case. Remarkable results are from curly hair and straight hair. The reductions are more significant than the others. I believe this result emphasizes the method can efficiently reduce the number of intersections with such thin and tilted geometries. One more interesting insight is that we observed higher resolution tends to have better reduction, but there is no memory size difference. So it also shows that the LUT-based compression for voxel mask works very well. We saw some intersection reductions, but what about the entire performance? The configuration here is that voxel resolutions are same, the 4x4x4 and the 6x6x6. And for object mask, in this case, we naively keep 8 bytes and 27 bytes respectively without compression to focus the culling algorithm itself. And for culling, we use a LUT-based approach. The table here shows relative rendering time. Lower is better. For example, 90% means the raycast took only rendering time only takes 90% of time of the baseline. Unfortunately, we observed some machines get worse. However, specific to the hierarchies, we got performance improvements compared to the others. Here, 12% and 13% faster than the baseline with resolution 4K, and 13% and 14% faster than baseline with resolution 6K. So as a summary of our research, let me make sure our goals again. These are our goals. First, covers false positives more than AAVV. So our voxel-based culling reduce the number of intersections very well. Second, small computational overhead for culling. Our approach's overhead is cheap thanks to the LUT-based intersection, so that we saw performance improvements on specific scenes. Third, small memory footprint. Our LUT-based compression significantly reduced the memory size, but keep culling efficiency. Finally, we also proposed a simple occupancy approximation for efficient voxel build in BVH. It allows us to control the trade-offs between performance and accuracy. There are some limitations and future work. First, it's still hard to see improvement with all scenes with the current approach. It's not easy to achieve clearly since the ray tracing has been researched for decades, but this is an obvious future work. Second, dynamic scenes. Our voxel data representation in a hierarchy needs to be updated again after geometry modifications. So efficient handling of such dynamic scenes was considering in the future. Also, GPU measurement and optimization, which is also interesting to investigate since the memory access cost and arithmetic cost can be different from the CPU. We proposed the voxel compression algorithm, but it is still suboptimal due to the vast such space of the mask combination for a table. So further research may reveal more optimal algorithm to compress the voxel patterns. So yeah, this is left for future work. Yeah, that's all for my presentation. Thank you for your attention.
Thank you, Atsushi. There's time for a question or two for sure.
Hi, I have a few questions. For the overall perf measurements you were doing, it sounds like you're doing this on the CPU. What?
Yes, we measured on the CPU.
Okay, and the traversal, it's CPU traversal roughly matching the pseudocode you did for both?
Matching with, sorry.
Like you listed the two kind of simple traversal variants. Does your CPU traversal look roughly like that and then when you're measuring overall perf, is it just end-to-end time of the traversal loop?
No, we are measuring entire performance, so not just the focus only on intersection. We measured all entire rendering time.
Rendering time, not including build, I'm assuming.
Technically speaking, some initialization included, but we measured much longer rendering time. So the such a initialization or other overhead can be negligible.
Okay, and thank you. And then when you're measuring a loss on some of those scenes, did you find a clear area where why you were losing on those scenes, or is it not obvious?
Why some scenes get worse. Okay, so even if we use the hash-based intersection, it still take additional cost for arithmetic operations, memory fetch, and the bitwise end. Of course, it's, I would say, cheap, but also need to take in order to take this mask, we need to calculate the ray origin and the ray beginning and end locations, and combine as a key. Yes, this kind of overhead gives additional time, unfortunately.
That makes sense. I'm also curious if you've looked at all at doing something similar, but only for, say, the first few levels of the tree, so that you can get tighter bounds on major features in the scene, but not pay the cost on very small features.
So question is, sorry, could you repeat the question?
If you looked at say for the first several levels down from the root of the tree, do the tight voxel culling there, but not do it in close to the leaf nodes, so that you're paying less of that arithmetic cost, but you get tighter bounds on the major scene features.
Yeah, the box cells located every single node, so that culling is happening every steps of the intersections.
Right. Yeah. I'm just curious if it's possibly worth trying only doing the culling for the first few levels and not for the lower levels, if there's maybe a trade-off there.
Yeah, it makes sense. But it's not obvious where we should stop the this kind of culling. Maybe SAH or something as a heuristic may help. Yes, it's a very interesting idea.
Thank you.
Okay, let's move on to the next. I have some questions for it too, but let's move on to the next section. Keep it along, and we'll talk to you offline. A really nice talk.
Thank you so much.
Our next speaker is Daniel Meister, also from AMD, also from Tokyo.
Yeah, you can just flip it on or slide it in your pocket.
Center of Graphics again. It's has a long history in ray tracing. Those of you my age will remember. And he's doing some empirical tests that, as far as I know, are unique. The empirical work on what's fast and what's not is increasingly important, since theoretical stuff doesn't affect predict things well anymore. So I'd like to see this work, and please carry on, Daniel.
Thank you for the introduction. So yeah, let's start. Yeah, I will present our paper, Performance Comparison of Bounding Volume Hierarchies for GPU Ray Tracing. So let's start with the motivation. A lot of research has been done on ray tracing in the last decades. But the proposed methods are typically compared in very limited setups, so against one or two reference methods, and there are often shortcomings that, like, the methods are orthogonal, which might not be always true. And experts in the field sometimes really cannot say which method is the best. So our contribution is an empirical comparison of most popular BVH-related methods in a unified framework to make it as fair as possible. And we also proposed a small extension of insertion-based optimization. Yeah, so bounding volume hierarchy, or BVH in short, is the most popular acceleration data structure for ray tracing nowadays. It is a hierarchical data structure with geometry primitives, so typically triangles in leaf nodes, and bounding boxes or other bounding volumes in interior nodes, tightly enclosing the geometry in the corresponding subtree. And the ray traversal, or how we find the nearest or any intersection, works in like very simple way. So we start from the root. We test the root bounding volume, and if we hit the bounding volume, we have to go recursively into its children. We see that the green node was not hit, only the orange node, so we can skip completely like the green subtree, and we just go to the orange one. And we see that the gray triangle is the nearest intersection. So it's very simple concept, but the BVH construction itself is relatively difficult problem because there are many possible BVHs for a given input geometry. So we would like to somehow express the quality of a particle BVH. And to do that, we use something called surface area heuristic, SAH in short. And thanks to this heuristic, we can define a cost function, which is defined recursively for leaf node. It is just number of primitives in that leaf node times the CI, which is user defined like intersection cost constant. And for interior nodes, it is the traversal constant plus the cost of child nodes weighted by these surface area ratios, which somehow expresses the probability of hitting child node when the parent node is hit. So this is nice for the explanation, but for more practical computation, we can get rid of this recurrence. So we can get this expression, which is also very interesting because there are two terms. One is cost of leaf nodes and the cost of interior nodes. And sometimes we use just one triangle per leaf. So this is one. And if we use one triangle per leaf, this also the leaf nodes are constant, CI, CT are constant, and also root bounding box is constant. So only varying part is this sum of surface areas of interior nodes, which is also sometimes exploited by some optimization algorithms. Now I would like to briefly introduce or describe the algorithms we use for the comparison. So there are mostly like BVH construction related algorithms. There are three categories. This is the first one, fast BVH construction. So the first algorithm, LBVH, is very popular algorithm, very fastest algorithm, like in general case based on sorting primitives along the Morton curve, which you can see here on the right side. And it's very fast, but the quality is rather low because there is no any optimization of that cost function I described on the previous slide. And what is nice is, like this Morton curve, defines like a uniform grid or discretizes the space into a uniform grid, but it also encodes an implicit BVH constructed by spatial median splits. That means that the most significant bit corresponds to the topmost split, which is this one. The next split is this one, etc. So very simple and very very fast, but the quality is rather like inferior. So that was the motivation for the next work, HLBVH, hierarchical linear BVH, proposed by Granza and colleagues. And they use like the most significant bits, the prefix for the top levels and the rest for the bottom levels. The bottom levels are constructed in the same way as LBVH does. And the top level is constructed by binning. So it's like a top-down approach. And the binning is done with the clusters. So the prefix defines clusters. So the triangles with the same prefix, they belong to the same cluster. So that's another like acceleration thing. So this improves the quality, but it's slower. It's slower. Slightly improves the quality, but it's still slow. It's still fast, but like slower than LBVH. Because the LBVH can be reconstructed in one single kernel launch, unlike HLBVH. So the next category is called balance BVH. Balance means balance like good quality, and it's still quite fast. So first algorithm is block or parallel order clustering that we proposed a few years ago, and it's bottom-up approach. So it starts from the individual primitives, merging them into larger clusters. And we repeat this until only one cluster remains, which corresponds to the root node. It is, yeah, quality is pretty good. And it's also very fast, especially this optimized version proposed by Benton and colleagues, Block++, last year. And the second algorithm is slightly slower, but the quality is slightly higher than for Block. And this is first optimization algorithm here. So it's not construction. It takes an existing BVH and improves its quality. Typically LBVH, but it can be any BVH. And yeah, ATR TR is 3-watt restructuring, and A is agglomerative clustering. So it again uses agglomerative clustering, but in a different way. It starts from the individual primitives and it proceeds up to the root, and where there is enough number of nodes, we form a 3-watts and we reconstruct these 3-watts in parallel. And then we go just one level above and again form a 3-watt and reconstruct the 3-watt and so on. And this overlapping is really important for this quality. So it's really because you can propagate the changes up to the root. The last category, high quality BVH, where we really aim at highest possible quality, highest possible acceleration. There are two algorithms. One PR BVH, parallel reinsertion, which is parallel version of insertion-based optimization. And yeah, this is again optimization algorithm like ATR BVH, but in this case, the operation is that we identify a subtree which causes the cost overhead, and we remove it and we place it into a new position, decreasing the global cost. So it's more like these updates are more global than ATR BVH, but of course this limits somehow parallelism, so it's slower. But the quality is pretty good. So for example, we can move the orange node, the green node with its parent to a new position, like to the yellow node. So something like this we can do. And it's a like powerful operation because we can like place it into any other position in the tree. So the last algorithm, construction algorithm, SBVH, is, yeah, maybe we can say that it's orthogonal, but let's see. It's like the motivation is that the standard BVH is really, as Atsushi presented, like it's really bad at handling these like diagonal thin long primitives. So like if we have these two triangles, we can really do nothing about that with standard BVH. But for example, KD3, another acceleration data structure, which was very popular in past, it splits space rather than like separating primitive into two disjoint sets. So we can do something like this. So we have like no overlap, tighter bounding boxes, but we increase the number of references to geometric primitives. So now we have 4 instead of 2. But what SBVH does is that it tries like both splits, and it's like the one minimizing that like local cost approximation. Approximation is because we haven't constructed the tree, so we cannot really evaluate the full cost, so we do just the local approximation. So this is really good, especially where there are these nesty triangles. And the last technique, collapse. Yeah, so all these algorithms, construction algorithms or optimization algorithms, they produce binary BVHs. And we would like to also evaluate white BVHs, BVH4, BVH8. And to do that, we use this post-process collapse to convert BVH2 to white BVH. And we use the algorithm proposed by Elitia and colleagues, which uses dynamic programming to find the optimal conversion from binary BVH to white BVH. So yeah, so this is our small extension for the PR BVH, that parallel reinsertion. So yeah, so the original algorithm is pretty good, but it only accepts the changes which are improving the quality, which might lead to a minimum, which is typically a local one, which might not be the best one. Sometimes this is called hill climbing. So that's motivation to use to somehow explore the space more, to find better minimum. So there is a technique called simulated annealing. It's a general technique, and it accepts the solutions or the changes which can be also worse with a certain probability. So we can also accept with a certain probability this this change that temporarily increase the cost, but then we can find a better better minimum, which might be global or better local one or whatever. So yeah, so that's the idea of the simulated annealing thing. And we try to use, to combine it with this insertion-based optimization. Yeah, this is the acceptance probability, where delta D is the difference of the proposed change, and the probability is just this exponential. T is temperature, which is given by this expression. And intuitively, higher temperature means that the probability is high. So when the temperature is high, it's really like accepting almost all changes. But where the temperature is low, the probability is low of accepting changes which are worse. And when it is 0, it corresponds to the original deterministic algorithm, only accepting only better solutions. And the temperature looks like this. So it's clamped sinus function. And yeah, there are parameters, this frequency, maximum temperature, and it's scaled by the current iteration. So it's decreasing in time. And so always we have it's 0, then there is a heating phase and then cooling phase. So it's getting worse, and then we can try to find a better solution. And this is repeating. So that's the overview idea of this, our extension. There are some issues very specific to this insertion-based optimization. This was originally proposed for 3 rotations in the context of BVH construction or optimization. But the 3 rotations are quite simple. So there are 2, 4, or 6 possible rotations for each node. But in this case, we can really place the node into any other position. So in the original algorithm, so the space is huge, the search space is huge. And in the original algorithm, we use pruning, because we really cannot try all possible positions because it's too costly. So we use pruning. But in this case, we would like to also explore with a certain probability these branches which would be pruned otherwise. So we use something like stochastic pruning. So we use a similar probability for exploring these branches. And another issue is parallel processing. So there might be conflict if we do this in parallel. So like two threads can may want to modify the same node. So we have to somehow resolve these conflicts. Yeah, so there is no time to explain this in detail. So please check the paper if you are interested in this topic. Yeah, so if we have the constructed and optimized BVH, we want to use it. So the ray traversal, this would be very quick. So for ray traversal, we use this like seminal work by Ayla and Lane, understanding the efficiency of ray traversal on GPUs. It's a stack-based algorithm with persistent warps and dynamic fetch, meaning that when there are very few active threads, they will fetch new rays to get more occupied. So this is for binary BVHs, and for wide BVHs, we use work by Lear and colleagues, CPU style SIMD ray traversal on GPUs, which is very similar to CPU SIMD traversal, where each internal node, for example, is processed by multiple threads. Each thread is processing one of the child bounding boxes. And the last technique, ray reordering, I think also very interesting technique. It's somehow like a optional step before the ray traversal. So it tries to like group the rays into coherent groups, so like the similar origins and directions, which is good for the ray traversal because of memory accesses, decreasing the thread divergent control flow, etc. And again, we can use Morton curve, which is very like important concept in the BVH. Important concept in the BVH context. But this is more tricky because we also have to somehow encode the direction, not just the origin, which is not very clear how to do it. And of course, there's some additional overhead, like the sorting overhead. So speed up must outweigh this additional overhead. So this is our experimental setup. So our base framework is basically the ILAS framework. Like highly modified ILAS framework ported to HIP. HIP is a new kernel language and API for GPU computing, syntactically almost identical to CUDA, but it can be also compiled for AMD GPU. And yeah, we either use publicly available implementation of that algorithms I described, or also we implemented some algorithms by ourselves. We evaluated these methods on 12 scenes of varying complexity in the context of wavefront path tracing with next event estimation, 32 samples per pixel, 2 shadow rays per hit, up to 8 bounces, resolution 24 times 768, 3 camera views for each scene to make it less view dependent. So we averaged the times and the values over these 3 views, and yeah, all tests were evaluated on AMD Radeon RX 6800 XT, and each BVH is evaluated also in 3 branching factors, 2, 4, and 8. This is the setup of the BVH construction algorithm. So we have LBVH, HLBVH, block, ATR BVH. SAH is basically a top-down construction using the full sweep algorithm, so testing every single splitting plane between each primitives. SBVH and 4 settings of PRBVH, so like the hill climbing, the original deterministic algorithm, and simulated annealing, and the base is either LBVH or SBVH. So this is the first result. So here I report average results. In the paper, you can find the absolute values for each scene. This is the average over all scenes. And to do that, to make like some meaningful values, we have to do some normalization. So in this case, this is for the BVH cost. So lower is better. And we normalize it by LBVH of the corresponding branching factor. So here we have 1, 1. And yeah, the reason is to do that we really cannot compare cost of different branching factors because with increasing branching factor, the cost is decreasing because there are less number of nodes, internal nodes. But it's not really like this lower cost is not really reflected in the tracing times. And yeah, PR BVH can improve as BVH about 7% on average, which is also interesting. And yeah, unfortunately, only marginal improvement for simulated annealing. And spatial splits, yeah, as BVH, yeah, really improve, can really help, like about 13% on average. But what is more important is actual trace speed. This is for secondary rays. In this case, it's higher is better. And yeah, now we can like compare like trace speed between different branching factors. So now it's just normalized by binary LBVH. So this is 1, but this is not 1. Yeah, so PR BVH can improve as BVH in most of the cases, like very like marginally, like not in this case, but here or here. But simulated annealing, surprisingly, it's worse than just hill climbing with SBVH. And the reason is that, like, our explanation is that SBVH is top-down builder. So, like, top levels are like well optimized, and we believe that the reason why it is worse is that these top levels are destroyed during the heating phase, and they cannot be really recovered by that PR BVH when we again try to optimize the BVH after it's destroyed, basically. So that's our explanation. And yes, spatial splits really help like 24% on average, which is very good. But it heavily depends on a particular scene. So for finally tessellated scenes, it's like rather marginal. But for example, for PowerPoint scene, it's almost threefold. And what is interesting that the trace speed drops with increasing branching factor. But yeah, we use different algorithms for binary BVHs and for YBVHs. So that's I think that's the reason that somehow on AMD hardware this like binary traversal is more performant than that like SIMD CPU style traversal. And of course, it's not surprising that BVH8 is worse than BVH4 because you have to really store child bounding box in the node. So BVH8 nodes are really large, so you have to use some compression to compensate that, which we haven't used. And this is the same for shadow rays. So speed up is slightly lower, 12%, but still I think pretty good. And in this case, it's always better. Like we can still improve the SBVH. This is the last slide before the conclusion. Influence of ray reordering. Again, the values are normalized and averaged. And in the trace time, we include the ray reordering overhead in the trace time. And even when we do this, we can get a nice speed up, 7% for secondary rays and 8% for shadow rays. 8% for shadow rays. And again, it heavily depends on the particular scene. Typically, ray reordering pays off in closed, complex scenes where the ray traversal is costly, and there are many rays, so we can easily extract the ray coherence. And also, the sorting algorithm is getting faster with a large number of items. And on the other hand, it's not very good for object-like scenes where either primary rays escape the scene or like other rays are reflected by like after first bounce, and there are very few rays in these concave regions. So yeah, so that's all. Let me conclude the talk. So our contribution is this extensive empirical performance comparison of a collection of BVH-weighted algorithms. And we also propose this like minor extension of the PRBVH. And yeah, some observations. As BVH is pretty good, provides basically the best results, especially in this case, binary BVH. And it can be slightly improved by PRBVH. And the ray reordering has a potential. It pays off according to our experiments in most of the cases. So it has some potential. Yeah, so that's all. Thank you for your attention.
Thank you, Daniel. There's time for a question or two.
So let me start with a great amount of work on all the comparisons, great stuff. So my question would be something related to measuring performance of different algorithms. Something that I found very tricky in my experience is that often it is so heavily implementation dependent that one can fall into the trap of just even trying the best to fairly implement every technique and then realize that one particular algorithm can be optimized for certain hardware in a special way that suddenly changes the evaluation results. Do you have an intuition how much this could have been a factor here, or not really so much, because in the end all that matters is like the amount of visited nodes? What are your thoughts about this?
Yeah, thank you for the question. Yeah, I think the comparison in general is very difficult thing. So yeah, so I think the most important part in this context ray tracing and is what do you include in the timings, because sometimes it's not very clear so that's I think the important part for this it's really the same framework using the same timers and but of course, all these, yeah, as I said, some algorithms are publicly available implementation, so they are optimized for the hardware or the original authors used. So yeah, so of course, it's in this sense it's not 100% fair, but yeah, they are optimized for different hardware. So some, yeah, I don't know.
There's time for one more question. Okay, I'll take that one more question then. So do you think that this is settled, bounding by hierarchies is the way, and we can not bother to read about BSP trees or grids or anything else?
You mean whether PVH is the right structure, or we are done with the research on BVH?
No, it's BVH.
Oh, BVH.
So we should only research BVH.
Yeah, that's a good. Yeah, I think it's the right. Yeah, that's a good question. Yeah, I have to more think about it, but yeah, I think it's the right right data structure. Yeah, I think it's from these standard traditional data structures either KD3, BSP3, or grids. I think it's the best one in the general scenario. Of course, you can use, for example, grid for some specialized cases.
Like in the first talk, the grid is used.
That's BVH with a grid. Yeah.
Let's thank Daniel again. Our next talk is by Renee Karen from University of Clausthal in Germany. And it's on photon mapping, which is the algorithm that just keeps on ticking. If you want caustics, that seems to be the right answer for 30 years running. So we're going to see how to do it on modern hardware, which requires some good systems work and some algorithmic improvements. So take it away.
Yeah, thanks for the introduction. Yeah, I'm René Kern. I'm from the Technical University of Clausthal in Germany. And I present you accelerated photon mapping for hardware-based ray tracing, which was published in the Journal of Computer Graphic Techniques earlier this year. So photon mapping, as many of you know, is a global illumination algorithm, which especially excels at rendering caustics, which you can see in the glass at the bottom. So caustics are refracted or reflected bundles of light, often by highly specular materials. But most recent works for photon mapping and ray tracing hardware only focused really on rendering these caustics only. So we thought about how about building a GPU-based photon mapper with the new hardware that fully uses this hardware. And yeah, this is what we basically did in our work. We also used a very interesting collection scheme that exploits the ray tracing RPE and build a full prototype in the NVIDIA Falco framework. So before I start explaining our algorithm, I first go through some preliminaries. So first off, we have the normal photon mapping by Jensen, which is a two-pass global illumination algorithm. So basically in the first pass, the photons are distributed through the scene from a light source. And the photons are then stored on diffuse surfaces. In the second pass, we want to collect those photons. For that, we use camera rays. Like in path tracing, we shoot rays from the camera, and then on diffuse surfaces, we collect these photons. They can be collected via radiance estimate, which is seen here. So basically, for every photon, we calculate the BSDF and multiply it with the flux, then sum it all up and divide it by the area we collected the photons in. For Jensen's original photon mapping, the radius is fixed, and this can lead to some problems, as a bigger radius can lead to very slowly converging images. Luckily, this was fixed by progressive photon mapping from Hierarchies and colleagues. And we used further developments by Knaus and Zwicker, where they reduced the radius progressively with each iteration using this formula. So basically, I is the iteration number, and alpha is the value between 0 and 1. And Kaplayan and Daxbacher showed that an alpha value of 2/3 is optimal. Of course, to collect these photons, some sort of acceleration structure is needed. Normally, KD3s or hash grids were used for that, but as I mentioned earlier, we used an interesting new scheme that exploits a bit the ray tracing API. So Evangelou and colleagues recently introduced a rather interesting radius search operation. To explain it better, I first show you the normal radius search operation. So normally we have a query, and we want to collect all points that are inside a radius around this query. So now for inverse radius mapping, this radius mapping is inversed. So now the radius is mapped through to each point, and our query will now collect all points where it's inside the sphere. So to imagine it in 3D, our points can be imagined like real 3D spheres, and our point is just some point in world space, and we want to collect all spheres. And we can exploit the ray tracing framework with it by just using these spheres as real geometry and an acceleration structure. And our query is now a very small ray. This can basically be done because of two things. So for one, the ray is also called if we are inside geometry. And the second thing is that the initiator is called sequentially. So we can, is sequentially called for one ray. Also, spheres are not supported by the ray tracing API, so we used exoskeleton bounding boxes with a custom intersection shader instead. Yeah, and combining these two techniques, so the probabilistic progressive photon mapping by Knaus and Zwicker and the inverse radius search by Evangelou, we get our baseline progressive photon mapper. There you can see the pipeline, and I will now go through each step of it. So first off, we have a camera tracing path where we just trace like a normal photon mapping the camera from the camera and stop on the first diffuse surface. On this diffuse surface, we then store our hit point inside a, for example, geometry buffer or visibility buffer. Then we have our next step, the photon generation, which is also like normal photon mapping, where we just shoot our rays from the light source and then store the photons on the diffuse surface. And these photons are stored as axis-aligned bounding boxes and then given to the acceleration structure, to the RPE to build the acceleration structure. We also need to store auxiliary information like the photon direction and the flux as we need it for the BSDF calculations, which need to be stored at the same index. And then we have our last part, the photon collections, where for each previously traced camera point, we will use the inverse radius search to collect these photons. So basically for the small radius shot and for each photon that is inside, we can calculate the BSDF and flux and the any hit shader. Because it's called sequentially, we can just sum this up in the ray tracing payload. And after the ray tracing operation, we just divide by the area and we get our radiance estimate. Then of course, after each iteration, the radius is reduced. So this is the most basic version of our photon mapper, which basically is built on existing techniques. But we noticed some small problems with it, which we wanted to address and also address in our work. So the first problem we noticed is that on bigger scenes, many photons are not actually collected, but we still build an acceleration structure with it. That is a problem because that costs many computational time as well as memory, which we would like to avoid. So our main idea was here to just store the photons we actually see, because every other photon does not contribute anything to the end result. So we used a hash grid to remember the positions where we actually collect the photons. Luckily, we already have the camera information from our camera tracing path and can use this to mark this hash grid, to mark the cells where we actually want to collect the photons. Because the grid is static, of course, we need to mark multiple cells. So the grid is in world space. And to ensure that we need to mark as less grid cells as possible, we said that the size of the cell needs to be at least the size of the photon diameter. In that case, we can ensure that we need a maximum of 8 cells in 3D. Of course, the cell can be bigger, and sometimes this is also better because too small cells can lead to some problems. Yeah, so we mark these cells. So each of these cells corresponds to a hash because we don't want to actually store a real 3D grid. And yeah, it's a very simple hash map in just an R8 texture, and we store 1 if we want to store the photon at this point. Then on the photon generation path, each time we trace a photon and we want to store the photon, we just look the cell up in our hash map. And if the bit is set, the photon is stored. So now I will show an example of this. So here's the Amazon Lumberyard Bistro scene, and here's the full photon map of the scene. And we now want to look only at this small camera perspective also marked in this red box. And for this perspective, storing the whole photon map and building an acceleration structure with it would be wasted. So with culling, with our photon culling, only the small portion is actually stored in the photon map. And as you can see, this reduces the photon count drastically from around 700,000 photons down to 3,000 photons, which saves around 3 milliseconds building time, acceleration structure building time, which is huge. Maybe you also see these many small dots in the photon maps. These are two kinds of photons. So for one, these are real reflections, which are caused by the little glass bottle in the top left corner. And the other part are false positive photons, which can happen due to the hash mapping, because multiple grid cells, of course, can correspond to the same hash map entry, and therefore some false positive photons are stored. But we tested that any sort of collision detection would take more time, so we just built in the map with these couple of false positive photons. We also did a performance analysis with our photon culling, and basically the main conclusion is that on the bigger scenes like the bistro, the living room, or the bistro full, which is both lumberyard bistros combined, we can reach a speed up from 9 to 27%. Of course, this is always depending on the camera perspective used. So for example, if we use our perspective from the previous slide, the speed up will be greater than 9%. For smaller scenes, like for example, this caustic water scene where we actually see most of the scene, culling is of course a bit less effective, so it's slower because we have this additional overhead of creating the hash map. So to summarize, photon culling should be used every time we have a bigger scene. Our next problem was that we noticed on areas with high photon densities, like for example near lamps, our photon mapper got very slow. This is mainly because of two reasons. So for one, on these points, due to the high photon density, we have many any-hit shader invocation, which are worked at sequentially. So, and also in each of these any-hit shaders, we calculate our full BSDF, which depending on the material model can get pretty expensive. So our solution was to only evaluate a couple of these photons, so only a small subset, and make the any-hit shader as cheap as possible. So now we, in our work, we only wanted to evaluate for 3 photons, so a rather small amount. We stored these 3 photons in a list in the ray tracing payload, and in any hit shader, we basically just stored the index of the photon, and if the list was full, we use reservoir sampling to stochastically only store some of the photons. Sadly, we still need to trace all photons to get the correct reservoir sampling weight. So we need to look at least every photon once. Then after the ray tracing step, we do our BSDF calculations for these 3 photons inside the list. Visually, this was around the same. And performance-wise, especially on larger radii, so here's shown the linear radius starting from 0.10 in the bistro scene. And as you can see on a bigger radii, it was around 2 times faster, and it gets less effective as smaller the radius gets, which is because the smaller the radius gets, the lower the photon density gets, because less and less photons overlap with smaller radius. With our progressive photon mapper, of course, it starts with a bigger radii and which gets smaller relatively fast. But stochastic evaluation was still faster for the first 100,000 iterations for our settings in the bistro scene. But we noticed similar performances for every other scene. So basically, the stochastic evaluation is faster at the start of progressive photon mapping, and then we can fall back to the normal evaluation method, which is just evaluating the photons in the any shader. Luckily, these are easily swappable as they have the same inputs and outputs, so it's just swapping a shader out. And now here's a small demo of our photon mapper in the bistro scene. So as you can see, it has interactive speeds to move the camera, and then the image gets progressively better. Caustics are rendered. The photon mapper is rather fast, with around 13 milliseconds after a couple of iterations. At the start, it is a bit slower because of the bigger radius. We also can render the complex geometries like the cookies in the jar with no problem. To evaluate our photon mapper, we compared it with other photon mappers by Mara and colleagues, as well as Hajitska and Jensen, which we called hash ppm and stoch ppm in our paper. Comparisons of the collection scheme with KD series was already done by Evangelou and colleagues. So we focus on hash photon mappers, as they are most of the time faster for GPU cases. We compared the structure similarity index of our photon mapper against the other. And basically, I don't want to go too much in depth for the performance analysis. You can look in the paper for that. But the main conclusion is that our photon mapper has at least the same quality as the hash photon mappers and is around 2 times as fast, at least. We also did performance analysis for each part of the passes. So the main speed up point is the collection. So the collection with our ray tracing acceleration structure is way faster than collecting photons via hash grids. Even though we have the additional cost of computing an acceleration structure. But due to culling, this cost gets rather small for the bigger scenes. The generation is also a bit faster because just storing the photons inside a buffer is faster than inserting them into a hash, mainly due to cache coherence. We also did analysis over time, where interestingly the hash photon mapper gets slower over the iterations as the radius gets smaller and smaller, while our photon mapper gets actually faster over the iterations. So the smaller the radius, the faster our photon mapper gets. But you don't want to start with a too small radius, because then you will have noise all around. Also, we compared our structural similarity over time, and we also saw that our photon mapper was constantly better than the hash ones. So to conclude our work, we developed a hardware-based progressive photon mapper with real-time camera movement that is faster than existing hash-based techniques. We also introduced 2 novel techniques to our techniques, which is for one photon culling, where we discarded photons that are not actually collected, as well as stochastic evaluation, which especially speeds up photon at high photon density areas where, basically the many photons overlap. For future work, we can imagine that parts of our algorithm or parts of this work can be used in similar algorithms, such as final gather or vertex connection and merging, to speed things even more up. Also, it would be possible to combine our photon culling with, for example, photon guiding by Gridman and colleagues to get more efficient photon paths. Basically, to just get good photon paths in the first place, so we don't actually have to discard as many photons. Also, because our photon mapper is pretty fast, real-time global elimination is imaginable, but then some kind of filter would need to be used. We have full source code available under the Journal of Computer Graphics website or our GitHub, which is also linked on the website. Yeah, thank you for your attention. And if you have any questions, feel free to ask.
So great work. So I wonder what's the how is the quality affected by this reservoir sampling thing?
Actually, not that much. It's around the same. It's
But
negligible.
would it be significantly worse if you have complex material or very glossy surface?
Yeah, because we don't actually collect many photons on glossy surfaces.
Yeah, I mean moderately glossy or some material that have pretty weird shape of PSDF. Will that impact the quality?
Yeah, I don't think that they will be much affected by the stochastic evaluation. So in all scenes we tested, there was no noticeable artifacts or anything with stochastic evaluation.
Yeah. But most of the scenes are diffuse. I mean, most of the things are diffuse.
Yeah. So yeah, many parts are diffuse.
Try some really complex material or glossy things. Try to collect photons. Try to do the density estimation of glossy surfaces. Maybe you can see some difference.
Yeah,
I don't know.
Yeah, we would need to test that again.
Yeah.
Thank you.
Other questions?
This is not my area anymore, but I couldn't help but ask a question. I like it so much. Have you considered, I'm not sure if you've considered, but what are the roadblocks for taking the radius query and turning it into a nearest neighbor query? Will that just tank performance completely?
Could you reformulate that? I'm not sure I understand correctly.
So when you're fetching photons, you can either say I want all the photons within a certain radius, or you can ask another question, which is what is the photon that is the closest to my query point at the moment?
Yeah.
And my understanding is that it may not work with inverse radius search to do a nearest neighbor query. Maybe I misunderstood.
No. Yeah, nearest neighbor search should not work. Or rather, we did not test. So maybe it is that the ray tracing RPE first calls the nearest intersections, but I think it don't. So nearest neighbor search could not be performed with this inverse radius search.
We have time for another question.
So this is a super low-level question. During your talk, you were talking about you weren't able to use spheres, so you did this axis length bounding box.
Yeah.
But you used a custom intersection.
Yeah.
So
I used.
You could have done a sphere there. Was there a reason you went for AABB rather than a sphere?
I mean, there aren't spheres as normal geometry for the framework, or are there?
Well, because you were using a custom intersector, you could have written a sphere intersector rather than AABB.
Yeah, we used an custom intersection shader.
Okay.
Sorry.
So I misunderstood.
Yeah.
Another question?
What's the meaning of the frame rate counter in that corner?
The mean, or?
Yeah, the meaning, like, is it like anyhow reflecting of the desired quality, or like what is it? How to interpret it?
Yeah, it's just a frame rate counter from the FICO framework. Yeah.
Yeah, but when you're moving, it reflects, it freezes the scene, and then like when you let it go, it starts accumulating with the frame rate. So what's happening in the background? Like, what does it actually count?
Yeah, so the thing is, at the start, the photons are bigger, so more photons overlap, and the performance is worse. And as we showed on this graph over time, so it gets faster. So the performance increases, so the FPS increases over time.
Thank you.
Any more questions? I'm going to take chairman's prerogative and take the last question. You said that future work was interactive low illumination, but For progressive refinement, it looks like this would be a good tool right now to do architecture or film preview rendering when you're moving stuff around. Have you looked into people using it like right now for some existing applications?
So actually, we worked a bit on real-time global elimination using many parts of this work already. I don't want to talk about too much because we have a paper in work for that. So so it is possible, and we looked into some other works also, which we could combine with our photon mapping.
That's great, because one of the most interesting things in the talk to me was the progressive refinement looks good. The blotchiness doesn't seem to bother me at all. So it seems like a very useful tool now.
Yeah.
I guess since you put the code up there, I could find out myself. Okay, thank you again. Our last session is going to be virtual. It's by Zihao Liu, who's a Huawei, and he is going to join us for a Q&A after the video presentation.
Hi, welcome to this presentation on our paper, Important Space Ray Strategies for Dynamic Diffuse Global Illumination. I am Zihao, and I'll be presenting for our paper. I would like to thank my co-authors, Jing, Helen, Jim, and Jerry for their help on this project. Global illumination computes interaction among lights, objects, and materials, provides direct and indirect illumination, and simulates effects such as indirect color bleeding and soft shadows, as shown in these images. Real-time global illumination has stringent frame rate requirements, usually between 30 and 60 FPS. One of the solutions is through path tracing, where it provides ground truth image reference for most real-time rendering approach. However, most real-time solutions on path tracing can only afford a few rays per pixel with a limited number of bounces in real time, due to the fact that incoherent rays and further bounces are expensive to trace. Furthermore, path tracing requires an additional denoising step for post-processing due to limited sample count. Despite the emergence of real-time path tracing solutions on discrete GPUs, it hasn't yet been scaled to most consumer-grade desktop GPUs, mobile, and virtual reality hardware. Therefore, we need an efficient real-time GI solutions on these GPUs as well. Dynamic diffuse global illumination, or DDGI, simulates diffuse indirect illumination in real time while avoiding light and shadow leakage. Probes are distributed throughout the scene to collect irradiance and visibility information for diffuse shading using ray tracing. Each probe traces a fixed number of rays uniformly on its probe surface, whose performance is independent of display resolution. The drawbacks with DDGI is that, first of all, it retraces rays into the scene without any reuse of gathered ray samples from past frames. Second of all, it allocates rays on the probes uniformly regardless of dynamic scene changes, which leads to oversampling unimportant scene regions and undersampling important scene regions. This is especially the case with the bottom right figures, where we see that the scene might be static and then there are tons of probes allocated in the scene. Reusing the past ray samples can provide a significant amount of savings in the GPU time. We introduced important sampling for DDGI, or ISDDGI, with a dynamic ray allocation strategy that redirects computational resources for probe ray tracing to emphasize certain scene regions, similar to the important sampling in the path tracing work. We extend the original technique to add ray strategies that account for dynamic behaviors of the 3D scenes and reuse history ray samples. ISDGI probes sample scene changes based on light and object movements. There are two types of rays. One is a uniform rays, where to collect the external scene changes, and the dynamic rays, as highlighted in these yellow boxes, to collect the scene changes based on the temporal visibility from the object movements or temporal irradiance changes from the light movements. Our contribution is set of important space ray strategies for real-time DDGI computations, and adapted historical and temporal frame-to-frame analysis for smooth shading transitions and fast visual convergence, and a set of GPU-based optimizations for efficient reallocation and utilization of memory bandwidth. And we also provide quantitative visual and performance comparisons with the DDGI. And we highlight that most speed up of our approach comes from the probe ray tracing stage. Light maps computes light information using a precomputation in a scene and store into textures. And then this light baking process can be time-consuming. Light probes helps avoid these pre-computation and handles light object interactions dynamically. And then probes can encode overall light field and visibility and can even render view-dependent GI effects but through the cube maps or spherical harmonic expansions. However, the performance with these early light probes are limited in complex dynamic scenes. Probe placement has like a uniform probe placement approach that suffers from light leakage. Non-uniform probe placement addresses this by taking into consideration of the scene geometries. Our I3D work with any probe placement technique. For real-time ray tracing, the development of real-time ray tracing hardware propels the progress of dynamic real-time global illumination, such as Research and Research GI. Our ISDDGI approach also uses ray tracing to sample scene changes and collect ray samples. Our work is built around DDGI and multiple important sampling. For DDGI, it consists of several stages. It begins with the probe ray generation and ray tracing, where probes obtain the ray samples from the scene. And then the hit distance is used to analyze whether probes are inside or outside geometries by assigning probe states. For the integration, then, probe ray samples are used to compute the irradiance and visibility for shading. Finally, the shading point samples adjacent probes and perform these normal distance visibility tests with minimal light and shadow leakage to shade diffuse surface. Multiple important sampling provides an unbiased method for reducing the variance of multicolor estimators, and combines multiple strategies where each sampling strategy estimates well in different regional domain but is insufficient for the overall domain. There are several combination strategies, including balance and power heuristics. The original MIS work is used to improve path sampling quality for path tracing with better rendering results given the same amount of ray samples. Our usage of MIS, on the other hand, is to enable probes to sample scene changes efficiently and improves overall rendering performance on the GPU. We use the temporal approach by utilizing different update state strategies for static and dynamic elements in the scene. We reuse collected ray samples in the past for static scene elements. We update probes' internal knowledge of the scene by collecting scene changes where there are dynamic geometry and light movements. As shown in these figures, the red texel means there are rays allocated in that direction, whereas the blank texel means there isn't any ray allocated. We reuse the ray samples for these blank texels during the integration, and then update ray samples for the integration for these red texels. And then for the probes near the scene changes, we are allocating additional rays in order to react to these changes, as shown as the probes near the boxes. We derive visibility and irradiance probability density function to measure scene changes around probe by computing the temporal delta of these irradiance and visibility between two adjacent frames in every ray direction. Then we compute the distribution of these temporal differences on each probe. This distribution informs our ray allocation to ensure our rays are sent toward detected scene changes. So our pipeline consists of initially tracing a few uniform rays on the probe to collect external scene changes. Then by computing the temporal deltas of the irradiance and visibility, we generate these PDFs for ray allocation, and our ray tracing essentially traces both the uniform and dynamic rays into the scene to collect ray samples. Finally, our integration uses both the current frames samples, collected samples, as well as those we used from previous frames in order to produce the shading results. There are several benefits. One is that our approach maintains similar visual quality to the original DDGI. And second of all, our approach samples ray directions with significant scene changes to ensure fast visual convergence by using spatial temporal supersampling and adaptive temporal accumulation. And finally, our approach sends a subset of the rays of total ray budgets to sample scene changes compared to DDGI by using the MIS to combine these ray sampling strategies. Our uniform rays are uniformly distributed on probe surface to collect external scene changes. The amount of uniform rays are roughly between 1632 and 64 is often below the total ray budget, 256 of every probe. We show here like two cases where one is the 16 uniform rays and the 32 uniform rays, where 32 uniform rays probes have a more denser distribution of the ray allocated on the surface. Our dynamic rays are used to collect ray samples from scene regions with significant temporal scene changes. Its allocation is proportional to the PDF estimated scene changes around the probe. The number of dynamic rays is often bounded by the maximum ray budget available after considering uniform rays. However, in general, the usage of dynamic rays is often below the ray budget if there isn't any scene changes around the probe. We show here two cases with dynamic rays. One is due to the object movements, and the other is due to the light movements. We developed a probe model for how a probe samples scene changes with rays. We call a group of adjacent rays bundled together a direction set corresponding to a surface patch on the probe, highlighted as orange. Probe surface can be discretized into 256 direction sets. Every direction set covers a unit of shading sample on a probe's surface patch. And the direction set can be sampled with one or multiple rays in our case. Our final integration uses both the reuses both the history ray samples and current frames gathered ray samples to produce a irradiance visibility for every probe. As shown in this example, in the first frame, we trace 256 rays as there is no ray, there isn't any reuse possible. And when we arrive at the fifth frames, all these colored texels, other than green, are what's been updated in between these first frame and fourth frame. So in the fourth frame, we use both the green texel from the first frame as well as the rest of the texels updated after then to compute the integrated irradiance visibility. For our important sampling formulation, there are two main steps. One is to measure scene changes through temporal analysis of irradiance visibility. The other is to evaluate the distribution of these changes on every probe. Finally, we derive the final mixture distribution of the scene changes by combining these two sampling approaches with the MIS. To measure scene changes, we consider how we compute the irradiance of visibility by using the radiance and the hit distance gathered from the ray samples. And these irradiance of visibility are temporally accumulated using the hysteresis formula. To compute the temporal deltas of the state of the scene changes, we just compute the difference between what's being accumulated from the history as well as what's being computed using the current frames ray sample buffers. And these deltas naturally encode the extent of GI convergence over the last few frames. And they also, as we show in our paper, they also have a cosine distribution on the probe surfaces, which improves the robustness of scene change detection. To evaluate the PDX, we estimate the degree of total scene changes observed by every probe. It's expressed in an integral form and can be estimated using Monte Carlo integration. In order to minimize the variance of this estimation, we would like to obtain a ray sampling distribution for each ray sampling strategy based on the ratio between the measured scene changes over a specific direction set and the total amount of scene changes observed by a probe. Finally, once we have these ray sampling strategies, we combine them to derive the final PDF for the dynamic ray allocation. We use this MIS with balanced heuristic to estimate aggregate scene changes observed by a probe. And we show that our approach with MIS, we are essentially sampling the scene changes using a mixture probability density distribution function, combining the irradiance and visibility sampling strategies. And in general, uniform sampling and multiple strategies work well. We also introduce several ray strategies. One is a one ray versus multi-ray, where for every direction set, we either send up to one ray or 4 rays per frame to sample scene changes. One ray approach saves retracing costs and improves overall frame rate while providing similar visual quality to DGGI. Multi-rays increases the ray sample budget per direction set to further improve visual quality at additional cost of performance. Both approaches uses a total budget of 256 rays per probe in every frame. We also have the uniform ray allocation. We begin with a predefined uniform ray allocation to sample scene changes, where these uniform rays, as shown in these first two figures, are uniformly distributed over the probe surface. The left figure shows how it happens on the probe, where red texel means one ray allocated. The yellow texel on the ray allocation texture shows how it's allocated on these 16 by 16 ray allocation texture wrapped around the probe. And because the sample scene changes only at a specific directions, it has a light and shadow leakage during the dynamic scene changes. Therefore, we introduce uniform ray rotation, where we sample where a probe sample an exclusive subset of direction sets on the probe each frame by sampling all direction sets of the probe every 256 divided by the number of uniform ray frames. For instance, with 32 uniform rays on a probe, it samples all the ray direction sets in 8 frames, and then introduce around 0.1 seconds of delay. Based on our experiments, we found that allocating a number of uniform rays in 16, 32, or 64, or 128 for a probe is sufficient. And for the uniform ray rotation, these two test cases shows that what happens when we use without the rotation, when there's a scene changes, versus what happens with the rotation. And without the rotation, we see that after scene changes, there's a light leakage in this area. But with the rotation, our approach is able to converge the GI during these scene changes. And the way we implement this rotation is by shifting the ray allocation one texel to the right every frame and wrap around it. And we also address the aliases in the ray sampling direction among uniform rays from the 8-cage probes. And as a result, it could result in alias shading values. And the method essentially is by permuting the ray sampling direction of uniform rays among 8-cage probes. by considering the probe index into the initial predefined ray allocations. So once we add these random seed value to the predefined ray allocations, we are able to permute all the ray directions, similar to the inner leaf sampling in the image space. We also introduced adaptive uniform rays, where we vary the number of uniform rays on a probe in a spatial temporal way. Probes observing nearby scene changes will quickly react to them by allocating more uniform rays. Probes observing few changes will allocate less uniform ray to save ray tracing costs. As shown in the left figure, where we have the adaptive uniform ray feature, the faraway probes from the scene changes are able to allocate less uniform rays to save performance, whereas the probes near the scene changes allocate more uniform rays to help with visual convergence. Compared to the fixed uniform ray approach, we are able to provide additional ray savings in this regard. By combining our previously mentioned uniform ray approaches, we arrive at the following formulation for the uniform ray, where every direction set allocated at most one uniform ray. Our dynamic ray essentially is allocated after considering the uniform ray allocation for a probe. It essentially, we multiply the rest of the amount of ray budget with the mixture PDF distribution to compute the dynamic ray. For a random array orientation, our strategy essentially ensures each ray sample is contained within the surface patch of the corresponding direction set. This provides accuracy for ray sampling and scene change estimations. And both the uniform and dynamic rays are collected from scratch each frame. The final number of rays allocated per direction set is a summation of their values, capped by a maximum in order to ensure the real-time performance of our approach. Furthermore, as we show in our paper, with this formulation, the total number of rays allocated per probe can be shown to be bounded between the number of uniform rays on the probe and the total ray budget, dependent on the amount of scene changes around the probe. This shows the pipeline of for our ray approach ray strategies for ARM probes, where we allocate uniform rays and dynamic rays in the ray allocation stage. And the dynamic ray takes into consideration of the irradiance and visibility delta computed between two adjacent frames. And these ray allocations are informed the rest of the DDGI stages. For the ARM probes, we are only allocating small amounts of uniform rays. And as our method might trace from 0 to up to 4 rays per direction set on probes, we need additional ray management in the DDGI stages. As shown in this figure, the bottom probes has 4 rays. Some of the direction set on the bottom probe has 4 rays allocated, highlighted in yellow, and 3 rays highlighted with cyan, 2 rays highlighted in blue, and 1 ray highlighted in green. This is due to the objects moving past the camera, which enable the probe to see the visibility changes around it. So we introduce a light ray allocation stage to the beginning of the pipeline and modify subsequent DDGI stages to accommodate sending and integrating variable number of ray samples per direction set. We store rays compactly in a sorted ray buffer for coherent memory transactions, efficient ray traversal and acceleration structures, and guiding subsequent ray tracing efficiently with a variable number of rays per direction set. We highlight how we compact this in the following figure. And as we show that our compact buffer can produce this sorted and compact data for subsequent stages. Our pipeline initially computes a ray allocation image for the prefix sum of allocated rays, number of allocated rays per direction set. Then these buffer is used to compact the ray directions on the probe. And then based on this compact ray image as well as the ray allocation image, we update the ray samples image for every direction set after the ray tracing. It is complete. In our reallocation stage, we essentially compute 16 by 16 reallocation texture that are ordered by this sequence number. And then essentially it also contains our important sampling formulation for the scene change estimation with a mixture PDF. To compute its summations for the denominators, we essentially distribute the computation to 2 works. So our entire work group can then sum these sub-results and communicate it through the shared memory in the GPU. We also compute the following data, like the number of allocated rays, number of ray hits, prefix sum of these data for every direction set on this ray allocation texture. And then finally we compute the total number of rays and total number of ray hits for every probe. For the probe ray generation, we produce this compact ray buffer based on the ray allocation image. The benefits of this buffer is we use the same amount of storage space as the original DDGI approach. We also provide coherent memory reads and writes, coherent ray traversals and acceleration structure in hardware, and improve CMD utilization by tracing 1 ray per thread instead of a variable number of rays per thread. For probe ray tracing, we essentially send rays into the scene with a 1-to-1 mapping between a ray and a GPU thread. And our probe state update and integration stage uses all the valid rate samples on the probe. So for run rate, our approach has to iterate through all the direction sets on the probe once. And for multi-rates, the number of valid samples can vary depending on scene changes around the probe, and it's bounded between a minimum and a maximum, usually between, and it's between like a 256 and 1024. And our method also reuses rate samples from past frames to save ray tracing resources. So the probe can only dynamically send rays to a direction set observing significant scene changes. And we also have these adaptive hysteresis because we already computed this mixture PDF functions. So we can use this PDF to enable irradiance and visibility to quickly react to scene changes over a direction set. We built our methods using Vulkan SDK and GLSL shaders based on DJI papers from I3D 2019 and 2022. We use RTX support of Vulkan RT for probe ray tracing. Our methods add a few extra images and with a small amount of memory cost highlighted in this table with 1K, 2K, 4K, and 8K probes. For memory optimization, we use data encoding techniques to store fewer bits in the reallocation texture while preserving the same visual quality. We also encode ray directions using VEC2 offsets on the probe surface patch and reconstruct them using octahedral mapping. We pack multiple data together into single-channel image whenever possible. We launch compute workgroups that consume spatially coherent data instead of scattering the texture access. For our computing optimization, we use Vulkan subgroups to reduce data synchronization costs and share memory usage. We use these to compute the denominators of the PDFs, compute the prefix sums, and to compute whether a probe sees any local scene changes. And combine these memory and computing optimization provides 7.6 times speedup for one ray and 4.9 times speedup for the multi-rays, and is able to help us in reduce the GPU runtime of the ray allocation stage to less than 0.1 milliseconds with 4K probes. For test scenes, we run it on the Sponza with 262,000 triangles. We also create our Chinese street art assets that are art teams, including complex geometries, materials, and lighting with emissive features. These have up to 2 million triangles. And then we measure visual quality using the standard visual quality matrix using NRS, MSE, SSIM, and PSNR. Our performance evaluated using the GPU times, sequence of GPU times, and speedups are computed using the average GPU times. All probes except reference probes use 256 ray budget, and measurements are conducted on RTX 2070 Super. For the static scene, when we measure it in the Chinese street with 8K probes, we see that our ISDJI maintain a very close visual irradiance quality to the original reference approach. Our multi-rays provides a higher visual quality to our one-ray approach. And overall, these four approaches produce visually identical results with the diffuse radiance comparison as well. In the Sponza, with the 4K probes, we see consistent results across these visual metrics, and then the overall results also consistent within the other test scene. And then when we try to measure how the probes will react to the localized scene changes when there's only one object moving in the scene, in this case, our ISDJI one-ray multi-rays can produce similar results to the original DJI and reference, and then where our multi-rays further improve the visual quality of the one-ray. We observe a consistent results again in the Chinese street with the 8K probes with one dynamic dragon moving in the scene. Finally, in order to measure how the probes will react to the large-scale scene changes due to dynamic light movements, such as moving directional lights, we compare the irradiance of these approaches. Again, our ISDJI approaches produces visual quality similar to the original reference approach, where our multi-rays improves upon the quality of the one-ray approach. And we observe consistent and similar results in the Chinese street with the 8K probes. And then, as you can see, the diffuse radiance after multiplying with the texture albedo is basically these four approaches essentially are visually visually equivalent. In terms of performance, in the dynamic light scene in the Sponza with 4K probes, our approach highlighted in orange and green outperforms the existing DJI approach in terms of the total DJI total time, due to the fact that we are able to provide a significant amount of savings in the probe ray tracing stage, and then while introducing bounded overheads in other stages. We observed similar results in the Chinese street with 8K probes, where our approach outperformed the original approach in terms of the total DJI time, due to the fact that we are able to provide these significant saving in the probe ray tracing stage. And we introduced small amount of overheads in the reallocation, and also bounded overheads in rest of the stages. The overall speedups for our DDGI pipeline are 2.14x and 2.47x for one ray, and 1.27x and 1.46x for multi-rays. The overall speedups for probe ray tracing stage are 3.72x to 6.64x for one ray, and 3.29x and 4.4x for multi-rays. The reallocation stage is linearly dependent on the number of probes in the scene, and generally takes around 0.03 milliseconds for one ray and 0.07 milliseconds with the 4K probes. And we see a slightly double the runtime for the 8K probes. Overall, ISDGI maintains high-quality irradiance similar to DDGI while providing overall speedups for real-time diffuse shading. And there's also the other approach called ray reordering with a standard DDGI array distribution. The ray reordering appears in the I3D 2020. Well, it provides a way to optimize ray tracing, but however, the efficiency improvements at the probe ray tracing stage using ray reordering approach is going to be limited due to the ray retracing collected ray samples and the ray sorting cost. Our ISDGI not only traces coherent rays, but also reuses past ray samples, which provides significant savings for ray tracing. However, our limitation is that the ISDGI has flickering irradiance when light sources are scarce in the scene. A potential solution would be to use spatial variance of the gathered radiance at every probe to guide the ray allocation, similar to the gradient domain light transport work. And also, our ISDGI irradiance quality diverges by a small amount from that of the original DDGI. We could allocate more ray samples per direction step to improve this at additional cost of performance. As an example, we have this multi-rays approach that can improve their visual quality further. However, after multiplying with the albedo to get texture radiance, most of these visual gaps minimizes and they're almost invisible in our experiments. We would like to thank our artists Yang and Zi for creating art assets used in this project. We also thank Canada GFX team and Huawei Technologies for their support on this project. And with that, this concludes the presentation. I thank you very much for your time.
So nice work. So since your work is targeting optimizing the performance, right? But shooting less rays per probe. So have you tried to test with really low-end GPUs or even mobile devices to see how the performance compares?
This is a good question. I think we are for this project on the research project, we're actually just doing most of the testing on the desktop GPUs, and then we have there are plans to actually do the additional the testing work on the mobile GPU devices, but it is an ongoing work that we haven't released any information yet. But yeah.
Okay, thank you.
Yeah, thanks.
Other questions? I have a question. So you've pushed the performance of the probe construction. How far do you think you are to the limit? Like, how much headroom is left?
Thanks. This is I think this is a good question. I think in terms of optimizations, when we do the benchmark for the experiments, and then we try to apply optimizations for all of the considered approaches. I think there are like our approach and also the original DDGI with 256, and also we have this reference approach. So we try to do optimizations for all of them, and then try to compute how our approach can improve performance based on that. And then I think as far as the amount of rooms we have left, I think this is as far as we could get in terms of at least on these GPU models we have. But I'm sure as with newer GPUs, both on mobile and desktop, there are additional opportunities to apply these optimization techniques to further improve it.
Thank you.
Thanks.
Are there any more questions? Okay, my final question is, what time is it there?
I see. I think right now it's 3:11. Yeah.
AM.
I think I'm in Vancouver. I think it's in.
Oh, you're in Vancouver.
Yes.
Oh, okay. Your background confused me.
Okay.
Hey, let's thank our speaker.
Yeah, thank you so much.
And let's thank all of our session speakers.